All right, folks, welcome back. Let's get after this here. Differential equations practice test 2020. That means the actual test is near. One last time you get to hear me say this. All the cool kids call this Diff EQ, so feel free to use that as a nice abbreviation if you want. And then, of course, it's yours truly doing this work. I really like this practice test, folks. There are a couple questions on here that students tend to struggle with, and I hope that through my dynamic and engaging commentary, you will find these problems a little bit easier in the future. Okay, so we have a differential equation here. It's dy dx equals 1/2 of the quantity x times y. First thing I notice here is we've got no restrictions on x or y. We don't have anything in a denominator. We don't have anything under a square root symbol. So based on the differential equation alone, x and y can be any real number. All right, let's now move on to the first part of this question. On the axis provided, sketch a slope field for the differential equation at the indicated points. Before I do this, I like to make a table of values. I find that very helpful. So here goes. Now to find the values for the slope, all I'm going to do is multiply the x and y coordinates together and cut it in half. Okay, so those are my values for the slope at each of these different points. Let's go ahead and sketch these on the slope field. All of them that are 0 means we have a horizontal segment, so those are pretty straightforward. Now we have to make sure we're careful here. We've got some, like let's look here, the difference between -2 and -1, that slope. What's important here is that you show a difference between those two. Your slope doesn't have to be perfect. That's a slope of about -1, and that's a slope of about -2. It just has to show that this one is steeper than this one. Now here are the rest of the slope segments. Okay, there's our slope field. Let's move on to part B of this problem. It says solve the differential equation for y equals f of x using separation of variables. So you know that I've got a 4-step process that I like to use. So we're going to separate, we're going to integrate, and then we're going to rewrite. So let's see what that looks like here. Original differential equation, xy divided by 2, or 1/2 xy. Variables are now separated. Let's write our antiderivative symbol there. Time to integrate. Now let's rewrite this bad boy by exponentiating both sides. I've already tagged that as C sub 1, and the reason why is a little foreshadowing here. I kind of knew that this bad boy was going to happen, and we could just call that C. So now I'm ready to rewrite this whole thing. I have the absolute value of y equals some constant C times e to the 1/4 x squared. We can go a little further here, and I'm going to write this as just y equals C times e to the 1/4 x squared. And I have to justify that. I'm not just allowed to erase an absolute value symbol. So I'm going to justify that here. If y is greater than or equal to 0, then c will be greater than 0. If y is less than 0, then c will be less than 0. And that's basically taking care of the piecewise nature of the absolute value of y. Okay, now we've solved this. This is our general solution. And we're ready to move on to the next piece of the puzzle here, which is part C. Solve for a particular solution through 0, 1, and then sketch the solution on the graph. So in order to do that, we're going to sub the point 0, 1 into the general solution, which is y equals C times e to the 1/4 x squared. E raised to the 0 power is 1. So this works out very nicely. That just gives me a constant of integration of 1. I can now state the particular solution is y equals e to the 1/4 x squared. Now this isn't quite done. I've told you this before. Whenever you write a particular solution to a differential equation, you need to state the domain on which it's valid. We have no issues in this function with domain restrictions. We also identified no restrictions back with the original differential equation. So we're going to say that this is true for all x. And some people might say, that's not necessary with this function, but I would argue that it's a good habit to get into anytime you're writing a particular solution to a differential equation. All right, let's go ahead and graph this bad boy on the slope field. This was our initial condition, and we're going to kind of come off this way and just follow the pattern of those slope field lines. And there you have it. Let's now move on to part D, and this is one that I'll tell you, students tend to find this question tricky. Take a look at this. It says find this thing in terms of x and y. I hope you remember what this is, folks. Yeah, this is Leibniz notation for the second derivative. There was, and I specifically am reminding you of that, there was a question on the AP exam a few years ago where students missed it more often than the graders expected. And they think the reason for that was that it involved Leibniz notation for the second derivative. So I want to make sure that doesn't happen to you. Okay, so we need to find the second derivative here. I'm going to write this out very specifically in a very mathematical notation. You may not write it this way all the time, but I just want to make sure you understand where this is all coming from. So I'm showing you here that we're taking the derivative with respect to x of both the left-hand side and the right-hand side. This quantity right here was the original first derivative dy dx. So when we do that, we get the second derivative. Now be careful. I hope that you see this before I even mention it. This is a product. So we better be using the product rule here. We're going to have 1/2 x times dy dx plus 1/2 y times the derivative of x with respect to itself, which is just 1. So let's go ahead and simplify this here. Let's write this as, on the left-hand side, y double prime equals 1/2 x times y prime plus 1/2 y. Now, in this form, it is correct, but I want to share with you that it doesn't meet the requirements of the problem. The problem say write the second derivative in terms of x and y. So I need to substitute back in my expression for y prime, and that's from the original differential equation. So now I have y double prime equals 1/2 x times 1/2 xy plus 1/2 y. Let's go ahead and clean this up a little bit. Y double prime equals 1/4 x squared times y plus 1/2 y. And that will get you full credit for finding the second derivative in terms of x and y. Another tricky problem, part E. Let's take a look at what we're asked to do here. Determine the concavity of all solution curves for the differential equation in quadrant 2. Give a reason for your answer. Well, this is something we haven't been asked to do for a while, and we're at that point in the course where we can see questions from any different section of calculus coming at us. So when I see a question about concavity, I'm thinking that we have a test for concavity. And the test for concavity is we analyze the second derivative. We look to see if that second derivative is positive or negative. Fortunately, we have an expression for the second derivative. We just came up with it right here. So we're going to be able to use that. The next thing we need to consider is this. What's going on in quadrant 2? Well, in quadrant 2, x is less than 0, y is greater than 0. So that's going to factor into our decision. Let's go back and look now at y double prime. We have y double prime equals 1/4 x squared y plus 1/2 y. Now let's analyze each of the quantities in here separately. We've got this quantity, and this quantity. Well, x is less than 0, but we're squaring it, so that becomes a positive. Y is already positive. So these are all positive quantities. Because those are all positive quantities, when we multiply them or combine them, we will end up with the following. Y double prime will be greater than 0 in quadrant 2. So all solution curves will be concave up. Okay, so one thing that might be nice to go back and look at is we already sketched a particular solution. Does that match what we just said about concavity? And it sure does. We sketched this, and in that quadrant, in quadrant 2, it appeared to be concave up. So that's just a nice double check. Before I go on to page 2 here, I just want to mention one thing. The practice test here says you may use your calculator. Justify all answers, no justification, no credit. We always say those things, but the calculator one is particularly interesting. I'm going to be honest with you. I haven't decided yet whether or not this test is going to be calculator or non. In fact, in this practice test, there's only one question where I'll even use a calculator, and that's only to get an approximate answer. You should be able to do everything without a calculator other than approximate some of your answers with the work we do with exponential growth. Okay, that's it. We're going to shut this one down and then move on to page 2. All right, folks, let's get after page 2 here. Question 2 says, consider the differential equation dy dx equals x divided by y, where y cannot equal 0. Pretty simple first part of the problem here. Slope field for the given differential equation is shown. Sketch a solution curve that passes through the point 1, 2, and sketch a solution curve that passes through the point -2, -1. Note this means two separate curves. The reason I mentioned that last sentence there is I've had students try to do things like this in the past, and I'm like, oh boy, that clearly is not correct. So please don't do that. So this first one is pretty straightforward. We have the point A here, and we're just going to follow the slope field. Remember that slope field is also known as a directional field or a direction field, and the reason why is because it gives us the general direction of solutions on the XY plane. All right, so that one's pretty straightforward. We're done with point A. Let's now take a look at point B. And the first thing I want to do here is show you an incorrect solution. So please do not graph your solution this way. We come off this way and follow the slope field. And I know what you're thinking. You're like, wow, he's got a pretty steady hand there. I don't know what could possibly be wrong with this. It looks like he followed the slope field pretty well. But the problem is I completely ignored this restriction. Remember, y equals 0 is along the x-axis, and our solution cannot cross that discontinuity. We have to pick a single open interval that contains the initial condition and does not violate any restrictions from the differential equation or the solution. So what I have to do to make this correct is I've got to erase this top half and make sure I show a discontinuity right there on the x-axis. So we're indicating that the solution can go all the way up to but not including values where y equals 0. Now that is correct. Let's move on to part B. Part B says write an equation for the tangent line to the solution curve that passes through the point -4, 2. So I know what you're thinking. You've been thinking, we've been doing tangent lines for most of the year. We've got this format that Mr. Vass has driven home. You know, we remember that this is point slope form. So we're going to go ahead and write it out like this. But I just want to caution you here. First of all, we don't know what the function f is. All we know is its derivative. We know the derivative is x divided by y. So this notation, f of c and f prime of c, I don't like that because we actually we're not using that notation in the problem yet. We may in a few minutes if we ever solve for the function y equals f of x, but we haven't done that yet. So I want to write this in a slightly different way. And I'm going to go back and erase some of my work here. And I'm going to rewrite the tangent line equation like this. It's some y coordinate that we know plus some slope times x minus some x coordinate that we know. Okay, well, we know a couple of these things. We certainly know that the y coordinate we're interested in is 2, and that's given to us right here. We know the x coordinate we're interested in is -4. But what about the slope? Well, the slope we actually know, but it's from the differential equation. Remember, the differential equation is the instantaneous rate of change. So that's going to give us the slope at every point on the solution curve we need. We only need the slope at one point. We need it at -4, 2. So we're going to evaluate dy dx at -4, 2. And I'm going to go ahead and do that over here. Dy dx is x over y. That means dy dx at -4, 2 is equal to -4 divided by 2, which is also known as -2. So that's the slope of our tangent line. We're now ready to write out our full answer here. Please do not be tempted to expand this and write it in y equals mx plus b form. You know that's just asking for trouble. Okay, let's move on to part C. Part C says find the particular solution y equals f of x to the differential equation with the initial condition f of 4 equals -1. Remember, that means we have the point 4, -1, and state its domain. So let's do this. Here's our general solution. Now remember, we have to write our particular solution in the form y equals f of x. This is currently not a function because I'm stating that it could be both positive and negative, and we know that for a function we have to have a single output. I also screwed up my constants here a little bit. The reason why I tagged this one as C sub 1 is because when I doubled everything in the second line, this is a new constant. Okay, but I don't need to specify anything after that because I think I'm done with constants. So how do we now find the particular solution? Well, we have to sub in our initial condition. We're going to sub in 4, -1, and we're going to choose the negative value for the function because y is less than 0. When I solve this for C, underneath the square root symbol there, I need to get a value of 1, and I need 4 squared, or 16, plus C to equal 1. That means C equals -15. I'm now ready to state my particular solution. It's going to be y equals the opposite of the square root of x squared minus 15. Now, I know what you're saying. Hey, I'm done. Let's move on to the next part of the problem. If you left your answer like this, you would be wrong and you would lose points because you forgot to state its domain. So I need to go back and give myself an opportunity here to state the domain. So this will be for some range of x values, and we have to figure out what that range is. Well, remember, our original differential equation was x divided by y, and y cannot equal 0. So we have to make sure that this quantity under the square root symbol does not equal 0. In fact, it has to be greater than or equal to 0 if it's under a square root, but because it can't, we don't want y to equal 0, it strictly has to be greater than 0. So let's go ahead and see when that is true. This inequality is true when x is less than the opposite of the square root of 15, or x is greater than the square root of 15. So I've got a choice here. I have to pick one of these two intervals that includes the initial condition. Because the initial condition has a positive x value, I have to select a single open interval that contains only positive x values. So that's going to be this guy right here, and I'm just going to add that to my solution and state for x greater than the square root of 15. Now this problem is done. Boy, that seemed pretty easy up until that last piece where we had to specify its domain. Okay, let's now move into the last problem here. Looks like an application of our friend exponential growth. The number of bacteria in a liquid culture is observed to grow at a rate proportional to the number of cells present. Anytime I see this wording, I'm thinking about this. That famous differential equation that says the rate of change is proportional to the quantity itself. We're then given some conditions here. There are 1,000 cells present, there are 100 cells present initially, and then after 3 hours, there are 120 cells. So I really have the following points on my solution curve. I have 0, 100, and then I have 3, 120. All right, so let's go ahead and solve this one. We know that the solution is going to be y equals c times e to the kt, but I want to run through this for you just one more time. So here goes. All right, folks, there's our general solution. I want to make one other comment here. For this application, y is going to be greater than 0. We can't have a quantity of bacteria that's less than 0. So because y is going to be greater than 0, we can make the following change to our general solution. Okay, the absolute value of y is equal to y for y greater than 0. Okay, so now let's go ahead and solve for c and k by substituting in our initial conditions. We're going to start over here, sub in 0, 100. That gives me the value for our constant c as 100. Let me scroll down a little bit. Let's now sub in 3, 120. So I have 120 over 100 equals e to the 3k. I can rewrite that as 6 over 5 because 120 over 100 is 12 over 10, and 12 over 10 is the same as 6 over 5. That equals e to the 3k. And then I hope you know you can take the natural log of both sides and divide by 3 to give you the following. K is 1/3 times the natural log of 6/5. Okay, so we have all the pieces, parts we need here to write our particular solution. We're going to take this, and this, and write it as follows. That is our particular solution. Let's now go down and look at what part B of this problem asks for. At what rate is the number of bacteria changing after 1 day of growth? So there's a couple things here that are important to note. At what rate? And then after 1 day of growth. Let's comment on each of these. The rate is just y prime. And we know that y prime equals k times y. 1 day of growth, well, everything else we've done so far is in terms of hours. So this is going to be 24 hours. Okay, so we need to find y prime when t equals 24. Remember, y prime equals k times y. That means y prime equals k, which is 1/3 times the natural log of 6/5 times y. So now what we need to do is just plug in our value of 24 for t and evaluate this expression to get an approximate answer. When we plug that in, we're going to get something that looks like this. A growth rate of about 26.132 bacteria per hour. That's the instantaneous rate of growth, right, when t equals 24. This one, part B, folks, that's a confusing question for a lot of students, and it's really so much easier than it sounds. You just plug back in t to your y prime equals ky equation. Okay, that's it for the chapter, the Diff practice test. Good luck on the actual one.